Okay, now it's working. Hello, welcome. I'm going to talk about checking and translating type classes, and it's going to be an introductory talk on Haskell, I think. I mean, not introductory in the sense that I'm trying to teach how Haskell works, but I'm trying to explain in relatively basic terms how Haskell type classes work internally in GHC. And that's not the only way to think about type classes. GHC makes a particular implementation choice, but it helps because, I mean, that's the model that the compiler that we are most of the time using is working with under the hood, and understanding how GHC deals with type classes helps from time to time when thinking about designing your programs. So I'll start and jump right in with a simple question. What's the type of x1? Hmm? A bool?
Oh yeah, function. Okay.
We're applying not to x, right? We take an argument, we're applying not to it, so it should be a bool, and the result is an application of the equals operator, so that also returns a bool. Okay? What type is the equals operator being used at in this concrete instance? What's the type the equals operator is being used at? Bool to bool to bool. Okay. What's the most general type of the equals operator? For A to bool for all A? For all A that are in the equality class, right? So on these first few slides, I'm from time to time using explicit quantification just because I'm sometimes mentioning variables that refer to other lines, so I want to make it clear that here this is standing on its own. Okay. Now, there is a class, equality, that's defined roughly like this, and I have an equals method that has type A to bool, and then there is an instance of equality for booleans that gives a definition for the equals method on booleans, and that's why this function actually works intuitively. That's why we can use the equals method at the type bool when it has the most general type like this. Okay, second example. What's the type of x2?
Is it actually access?
Yes, that's a typo. You're right. I mean, this is a this is a scope error, but no, should be access on the left-hand side. Yeah. I hear a lot of mumbling. So who wants to say something? Somewhere here. List of A to bool. For any A? Oh, okay. Right. For all A, if A is in the equals class, list of A to bool. This is more interesting, I think, than the previous example for a number of reasons. And what's the type that the equals operator is being used at here?
List of equal A to list of equal A to bool?
List of equal A to list of equal A to bool. Now, equal A itself is a class constraint. It's not really a type. So you cannot have a list of equal A. So, but you probably mean the right thing. So it's used at the type list of A to bool, where the A is the A that we're calling the function with, right? So, okay. And this time, we still have this most general type, but the interesting thing is, if you like, that we're using the equality method at this type, list of A to bool, but we're ending up with the constraint of the form equal A on the function type, rather than, for example, with the constraint saying equal of list of A, right? So why is that? Because intuitively, we have an instance of this form that says if we have an equality instance on A, we also can form an equality instance of list of A. And there is a definition for that. And the compiler somehow magically applies this instance and simplifies the constraint that arises from this method invocation, namely that we should have an equality instance for list of A's, into one that still remains that says that we should have an equality instance on A's. Right? And this is this kind of reasoning that is very informal. We're going to try to make slightly more formal in the rest of this talk. I can't make it completely formal, then I would unfortunately need more than 45 minutes, but at least make some progress along those lines. Okay, so let's look at one more example, because it gets yet more interesting. So this is the actual definition of, or one actual possible definition if I haven't made more typos, of the equality instance for lists. And as you can see, there is a definition of the equality function or equality method, but there are also two occurrences of the equality operator on the right-hand side in the second line. And these two occurrences actually have different types, right? So the first one, this one here, compares the heads of the two lists, and it's being used at the type A to bool. And the second one compares the tails of the two lists recursively, and is used at the type list of A to bool. And even though they look the same and are right next to each other, somehow the implementation has to use different code in both of them, and it would be interesting to know how that works. Okay, so I'm going to talk about what's called the dictionary translation now, or sometimes it's called evidence translation for type classes as well. And as I said initially, this is the way that GHC translates type classes when it translates Haskell down to core and then to STG and ultimately to machine code. So this is one very useful way of thinking about type classes. We can later discuss that there are other ways of doing this as well. So the idea here is what we are going to do in this talk is similar to what GHC is doing, but not quite, because GHC is performing the type class translation at the same time as a lot of other translations. So GHC is first type checking a Haskell program and then translating it down to core. And core is much, much simpler than all of Haskell. And there are lots of other features that get desugared away and simplified away. We're just going to try to translate a Haskell with type classes into a Haskell without type classes. So keeping all the other features around. Okay. In particular, we're going to use data types, record types, and functions in order to model type classes and instances. Now, how does that work? So it's relatively straightforward, actually. If you have a class declaration like this one, where the equality class is defined, and it's actually defined with two methods internally. You have a method for equality and one for inequality. Then you get a data type definition, and we are calling the data type exactly like the class. And it's always a single constructor data type, so it's always a record type. And the constructor we are calling make EQ here, but you can choose any name you like. And we're going to use the same names as record selectors, as record labels in the equality class. Right. So this is just a record that has two components that correspond directly to the two class methods. If we have an instance, such as the instance for Booleans, and it doesn't really matter for now what the code might be that is given for these things, then the instance is translated into an actual value of this record type. So we're going to introduce something that has a name, and I'm always going to use names that are hinting at what they represent. So this is representing the equality instance for Booleans, and it is of type EQ bool, and it is a record of this type, so we're constructing it using make EQ, and it has a definition for equals and a definition for not equals that are coming from translating the definitions over there. Now let's look what happens to class methods themselves. I mean, this is just a special case of what we've already seen. In Haskell with type classes, equals has this type. If you look at it in isolation, you can apply it to any two arguments of type A as long as A is a member of the EQ class. In our version, equals equals, as we defined it, is a record selector, and it has this type, because the record it selects from is a record of type EQA, and then the thing it projects out is a function of type A to bool. So the double arrow in Haskell just turns into a single arrow during this translation, and that's very convenient, and that makes it very easy to actually think about this translation on the fly without actually going through all the details. If you just have a piece of code and you want to know how does it look internally, you just in your head replace all the double arrows by single arrows. And in fact, I mean, it doesn't only apply to class methods, it applies to all overloaded methods or all overloaded functions that double arrows just turn into single arrows. So let's see more. So method invocation. If we have an example, one like call to equals equals, where we use the operator on the Boolean type, well, equals equals is a record selector, as we have seen, and we have to pass a record of type EQ something, and in this case we want to use equality at the type Boolean, so we have to pass in the record of type EQ Boolean that we have just defined. Right. So I have to use prefix notation now because I need to pass 3 arguments to equals equals, unfortunately, right? But we're passing the EQ bool record as the first argument to equals equals, which basically gives us the implementation of equality on Booleans, and then we still have the 2 arguments as before. In practice, I can say at this point, if you have code like this, the optimizer will not let it stand like this, and that's good, right? If you statically know at what type you're using something like this, then this record here is completely known, right? It is just defined somewhere in the code, somewhere in the libraries, and this is just a selector function applied to this record. So the optimizer can inline this call and can just give you directly the implementation of equality on Booleans, reducing this overhead here. Right. So what happens if we have a constrained instance, like the instance on lists that we have seen? Well, that's very similar to what we had for the normal instance, only that also here, the double arrow turns into a single arrow, and the definition of the EQ list dictionary is not a record just on its own, but it's actually a record transformer. It gives us a way of transforming a dictionary that gives us an implementation of EQ on A into an implementation that gives us an EQ on list of A. And we see that we pick up an extra argument, EQA here, which has this EQA type, which can be used in the translation of these functions, equals and not equals. Okay, what's left? How do we actually deal with overloaded functions? It's in a very similar way. So if we look back at example 2, example 2 is a function that has a class constraint, as we have seen, EQ of A, and it uses this equality function here at the type list of A. And here the compiler has to work a little bit harder. It has to construct a dictionary on the fly using the EQList instance that we have seen before and the argument that we get from here. So we get the EQA dictionary as an argument to the function. We transform it into a list of A dictionary using the EQList transformer. Then we select the equality method out of it, and then we apply it. All good? Great. A few more cases. So classes actually have default implementations, and so does the equality class. And in fact, the equality class has a slightly strange default implementation where both the equality and the inequality method are defined in terms of each other. And these days you have a compiler pragma that actually shouts if you are not, if you just think, oh, then I don't have to define any of them. But at least you get a warning these days. And in earlier times, you could just do that, and the compiler was happy. And if you call any method, then you'll just have an endless loop. And you can still get that. I mean, it's not an error, it's just a warning. But so this is how it is. And you only have to give one of them explicitly usually, and then the other one is filled in for you automatically. That's the idea there. So this is also just normal code. If we translate it, then what happens? Well, we define the equality dictionary type as before. That's from the class. And the default definitions just turn into extra function definitions in the translated code that we have available. And when we then give instances that are based on these default definitions, then we can use these. So this is just treated as a separate function definition. So there is going to be a definition for equals, the default implementation of equals, which is itself having an EQA constraint because it's defined inside the EQA class. So it gets an EQA dictionary passed. And it gets its two arguments, x and y. And then it's implemented by calling not or not equals for the passed-in dictionary on x and y. And similarly, the not equals method is defined by calling equals. Okay. Now let's look at the most complicated of our initial examples, where we have been looking at the instance declaration for lists and the actual code thereof, where the equals operator is used at two different types. How is this translated? Well, this turns into a dictionary transformer, as discussed before. It gets the dictionary for EQA as an argument. And then, I mean, it's not necessary. I could have inlined this here somehow, but it would have become very ugly. So equals is defined essentially as the definition above in three cases. But of course, the two calls to equals are specifically dispatched to the right types now. As we had said, the first call is on type A, so the dictionary we're passing to the first call of equals is just EQA. And the dictionary we're passing to the second call of equals is on lists of A, so we're constructing a list dictionary again by applying the EQList dictionary transformer to EQ of A. Okay. And then the other interesting thing is that we can see how the default implementation is being used, because we haven't given an explicit definition for not equals. And what happens now is that for not equals in this dictionary transformer, we're just using the default implementation for not equals. Well, and we need to pass it the dictionary we're just constructing, so we need to pass it EQList of EQA. Questions? good? Okay. What about superclasses? So type classes in Haskell can have superclasses. What does that mean? So an example is the ORD class of comparable types. You cannot make any type you like an instance of the ORD class. The idea is that you can only make a type an instance of the ORD class if you already have made it an instance of the EQ class. And that's expressed by this constraint. So ORD A is only available if you also already have defined the Q of A. And then you can define additional methods there, like less than or equal, but actually the ORD class contains a whole number of methods that are also all defined in terms of each other, with compare being the most general. So what happens to superclasses is that they turn into additional record fields in the dictionary. So if we define the translation of ORD, we're getting a record that contains all the methods of the ORD class as before, but it additionally contains a method to select the EQ dictionary out of the ORD dictionary. And this implements the idea that whenever we have an ORD instance, we know that we also have an EQ instance. So we pack them up together. We pack the EQ instance into the ORD instance, which gives us a way to get back at an EQ instance if we have an ORD instance. And we can see that in action in this example here, which is a function that takes 3 arguments, all of the same type, and performs some comparison and equality operations with them. So it compares x with y and checks whether x is less than or equal to y in the first case, but it also checks whether x is equal to z. But it only has an ORD A constraint, and it doesn't need an EQ A constraint, because EQ is a superclass of ORD. So we can do with just the ORD constraint, and that's enough. But that also means that indeed in the translation, we're only getting an ORD A dictionary here, and by calling the less than or equal operator is easy because we just feed it the ORD A dictionary directly. But now if we're calling equals equals, we have to pass it an equality dictionary on A, and we have only received the ORD dictionary on A, so we have to explicitly extract the equality dictionary from the ORD dictionary using this selector for the superclass. Okay. There are also type classes in Haskell that are not parameterized over types of kind star, but over type constructors, over parameterized types. Functor is a classic example. If you define instances of functor, you're not defining an instance of functor for integers or an instance of functor for booleans. You're also not defining an instance of functor for lists of integers or lists of booleans, but you simply define an instance of functor for lists, right? For the unparameterized, for the unsaturated type constructor. Can define an instance of functor for lists, an instance of functor for maybe, an instance of functor for IO. And these classes also have methods. Now, how does the dictionary translation look for these? Similar, but we need one new feature, right? So we get a data type like before, a record type, which is now also parameterized by a type of higher kind, of kind star to star in this case, because it's a type constructor. And we have a constructor, and we have different fields for the different class methods. But the class method is mentioning other type variables, A and B. And this means that we also have to mention other type variables here. And this needs an extension or a language feature that is called polymorphic record fields, which these days is part of what you get if you enable rank n types. Right? So that allows you to use a for all quantifier in here. But otherwise, it's nothing special. Let us look at an example for this one as well. So this is also to practice everything that we've seen so far. This is a rather complicated example already. So what are we doing here? This is actually even slightly less contrived than the previous one. It's something that you might actually want to do in practice in a similar way. You're reading a line from the screen, so that's an IO string action. And then we're going to read the string into a maybe. So the read maybe function is defined in the text.read module and takes a string into a maybe of A as long as A is a member of the read class. And then we get a maybe of A out, and we're going to map negate, which is the numeric negation function, over the A. Right, so we have two applications of fmap here. One is looking inside of the IO and turning the string that we get back from getLine into something else. And the other one is looking inside of the maybe that we get back from read maybe and turning the numeric thing into something else. And the numeric constraint is implied by negate. So there are quite a few things going on. What are the constraints that we get? Read maybe requires its result to be in the read class. Negate requires its argument to be in the num class. And fmap is being used twice, as I said, but at concrete types, at statically known types, namely on IO and on maybe. So no functor constraint shows up in the actual type signature, but it still plays a role in the translation. So example 4 turns into a function that gets two arguments, two extra arguments, a read A dictionary and a num A dictionary. And we're going to produce an IO maybe A as before. And we're picking up these two dictionaries. And the first call of fmap is to the functor IO dictionary that is defined somewhere in the library. And the second call of fmap is to the functor maybe dictionary, which is also given somewhere in the library. And the call of negate is at type A, so we use the num A dictionary. And the call to read maybe is also at type A, so we also pass the read dictionary. Read is also strange in the sense that, certainly strange if you're coming more from object-oriented programming languages, that overloading in most other languages is always on argument types and never on result types. And in Haskell, you can, without problem, define overloaded functions and methods that are overloaded on the result type. And read is one such example. As I said, it turns a string into a maybe of A. But for the dictionary translation, it really doesn't change anything. Right? We just pass it the dictionary, and it turns into something. So that's one of the nice things of this translation, actually, that we've already seen throughout the examples that I've given, that really the basic ideas, they carry through. I mean, if we add in new things into the mix, like superclasses, we have to modify it slightly, but constructor classes essentially don't really change anything. It just works, right? Yes.
Don't you have to pass the num type in the return value, so you can further work on the A?
No, because we're getting an IO of maybe A back, this is right, and we have a requirement for a num dictionary. But if you use that further with other functions that are also numeric, then they need to get the num dictionary from elsewhere again. So this isn't, the result is not sort of an A wrapped up with a num dictionary, it's just an A. And if you use it in a context that again requires A to be numeric, then that other function that calls it needs another num dictionary. Right? Okay. Okay, so here's the summary. That's the correspondence, roughly. So type classes correspond to record types, instances correspond to terms of record types. Instances with constraints correspond to record transformers. Class methods correspond to selector functions. Method invocation means application to a extra dictionary argument, and an overloaded function is a function that takes an extra dictionary argument or more. Okay. So I briefly want to go into the type inference aspect. So the dictionary translation actually takes place as a part of type checking and type inference. And that's an interesting technique that you see in other type system fields as well, that you do something that's called type-directed translation. So you're looking at the types, and depending on the outcome of type checking, you're constructing parts of the translation. And I'm going to give only a very simplified view on how that works. So roughly, you collect all the constraints from the body of a function definition or declaration, and then you're running an instance resolution algorithm that tries to satisfy these constraints as far as possible using the available instances, and thereby you construct these dictionaries, these actual terms of dictionaries that you can insert into the body. And then you generalize the binding by introducing any of the unsolved class constraints on variables that remain as function arguments. Right, these are roughly the 3 steps. You collect the constraints, you try to simplify them using the instances you have available as much as possible, and then anything that's left, you just expect as extra function arguments. So here's an example, a simple example again. If we call show on the reverse of xs, right, then we first collect the constraints, and we need to call show on a list. So we need something of form show of list of A. Then we try to resolve, and we use the instance of the form show A to show of list of A to simplify the constraint show of list of A to show of A. But it's not enough to just simplify it. We also need to produce evidence of that simplification. And that evidence is exactly the show list function, right? And then we can't simplify the show A constraint, so we're just going to assume it, and we're going to build up the dictionary show list or apply to show A for that particular call to show. And then we're going to introduce the thing that we had to assume, the show A dictionary, as an additional argument to example 5. Okay. So the core of the type inference is this constraint resolution statement, and that's the only theoretical thing that I'm going to mention here. So basically, if you have 2 sets of class constraints, one being summarized as delta 1 and one being summarized as delta 2, you have this strange thing which is usually pronounced entails, and you can say, with this knowledge, I can infer that knowledge. Right, is a kind of implication, and as a byproduct you get an expression, a term, that is the evidence for this translation. So that is essentially a dictionary transformer from the dictionary on the left-hand side to the dictionaries on the right-hand side. So if you have an instance of the form EQA to EQList of A, that yields a statement that you can go from EQA to EQList of A by using the EQList transformer. And if you have a superclass constraint, that's the only other thing that gives you a basic rule in this calculus. And that's perhaps interesting because superclasses work the other way around. So if you have a class that says EQA double arrow ORD A, what it actually gives you is that from ORD A you can derive an EQA, right? Using the accessor into the ORD dictionary that selects the other one. And then you have all sorts of standard extra rules, like, for example, transitivity on this strange relation that corresponds to composition and things that correspond to function application and so on and so forth that allow you to use these basic building blocks that are given by the instances and the classes to build up larger dictionaries. Okay, so it can look more complicated, something like this. This is a derived statement you could get. From ORD A, you can derive EQ of bool of a pair of Boolean of A by using EQ pair applied to EQ bool and the ORD A dictionary, which is exactly the assumption you can make because ORD A is mentioned here on the left-hand side.
Instead of ORD A, EQ A ORD A or something?
Yeah, can you use the microphone?
Oh, sorry. I think in the last slide, isn't the ORD A, shouldn't you apply this selector from the ORD dictionary to the EQ dictionary first?
Yes. Yeah, you're right. Yeah, I actually carefully designed this so that there were multiple rules being applied, and then I didn't follow it through. Yeah, thanks for pointing that out. Yeah, so it should be EQ pair applied to EQ bool, and then the ORD EQ applied to ORD A. Okay, so now if you look at all this, then one of the things to realize is that all the seemingly random restrictions that the class system imposes on you in Haskell 98 and also Haskell 2010 are actually just designed to make the implementer's job relatively simple here. Yeah, they're all designed to keep this instance resolution relatively simple. So what kind of restrictions do we have? We can only use single parameter type classes. We can only use constraints of the form C of A in both types, signatures, and instance preconditions. We can only give instances for types of the form T applied to a sequence of variables. You cannot sort of give in Haskell 98 and also Haskell 2010 without extensions, you cannot give an instance for lists of Booleans or something like that. You can only give an instance for list of A for a class. And that means in particular that you don't have any overlapping instances, and there is no such thing as scoped instances. Instances always escape everywhere. And this is all in order to guarantee a number of interesting properties that are very convenient to have. So at most one instance per type, right? There are multiple ways to construct different dictionaries for a single type. You cannot make any wrong decisions. If there is a class that seems to help for the dictionary you want to construct, you can always blindly apply it. You can never figure out that that was a wrong turn and you need to backtrack and go somewhere else. And also that the straightforward algorithm for instance resolution where you just blindly apply everything that you can terminates very trivially and doesn't loop or yeah, right. So this is all good. But in terms of the dictionary translation, most of these language extensions that lift these restrictions partially are actually relatively harmless. So they make the instance resolution much more complicated. But in terms of the dictionary translation that we've seen, they're relatively harmless. So let me conclude the talk by giving two examples here. Multi-parameter type classes, for example. Well, that just means that the dictionary types can now have multiple type arguments, right? And the instance resolution becomes a bit more tricky because you suddenly have class constraints with multiple parameters and they may decrease at different levels, and reasoning about, for example, whether if you apply instances in a row, whether that all terminates becomes much more difficult to judge. But in terms of the dictionary translation, it doesn't really change anything. Rather than with data types that are parameterized by one argument, you're dealing with data types parameterized by many. And things like functional dependencies is purely a restriction on the which instances you can define and helps the instance resolution algorithm, but doesn't affect the translation at all. Flexible context and instances lifts all the restrictions on how instances can look and how classes can look, and type signatures, constraints and type signatures can look. But that can actually have rather strange effects, as we can show here. So if you define, if you look at example 2 again, which was this reverse thing, which we said has type EQ A double arrow A to bool, list of A to bool, you can now actually give it, and that corresponds to this definition, sorry. You can now actually give it an explicit type signature using a flexible context that says, I want this to be constrained over EQ of list of A, and that will change the translation. And now it will not construct a dictionary on the fly, but actually take the entire dictionary for list of A as an argument. And you can see that this strangely interacts with things like overlapping instances in a very subtle way, because if you use the original translation, this one, and you would have an instance for lists of booleans somewhere that is different from the generic list instance, then if you've already applied EQ list here, then you'll never be able to apply that specific instance for lists of booleans anymore. So it's really very nice to be in a situation where you don't have overlapping instances and don't have to worry about when you do these class reductions. But as soon as you have things like flexible contexts and overlapping instances, things become much more complicated, unfortunately. Okay, so this is the summary. Dictionary translation helps, in my opinion, quite a bit to understand how classes work internally, and it's an interesting example of type-directed translation. And it's also nice to see that it scales to all the type system extensions and all the class system extensions that GHC has to offer. The dictionary translation really rather seamlessly extends to all of them. And you can actually see it in action by dumping GHC core output, and I encourage you to do so. GHC core output can be a bit intimidating, but you can really see the traces of it rather nicely. Okay, thank you. I think we are running a bit late, but perhaps 1 or 2 questions should be okay.
Did I get it right in the beginning? You said there are other ways to implement type classes than dictionary translation. What would those be?
Okay, so a very straightforward way to implement type classes is to do actual what's called intentional type analysis, to actually perform a kind of pattern matching on the types. So that requires a form of runtime type information to be available, and it obviously has other disadvantages. But it is another very straightforward way to give a clear semantics to the notion of type classes that coincides with this. And then there are variations on these themes. But I think essentially the sort of dictionary translation and intentional type analysis are sort of the 2 big lines, and then you have lots of smaller variations of these. Okay. Oh.
How do type families fit into this?
Type families. Type families have type families are functions on the type level essentially. They have no trace at runtime at all. So there are computations that are purely performed during type checking to reduce one type level term into another type level term, but they're not. There's no runtime representation change going on. So they are really equal types that correspond to equal representations. So they are completely. They live in the core language that GHC produces. So in that sense, they do play somehow into this, because in the same way that you can observe the type class translation by looking at core, you can also observe quite a bit about what happens with type families in core, because there are coercions being generated in the core language between different types that are found out to be equal during things like type family computations or GADTs. But unlike class constraints that turn into a runtime evidence, these equality constraints that are generated in core for type families and GADTs have no runtime representation. They're completely eliminated at runtime.
When I have a tuple of constraints, like the complex constraint read and num, if you swap the order, does this change propagate to the code, generate code?
I actually don't know, but I would assume not. So there is this new feature of called explicit type application, and you can use this feature also to do things like specify explicitly what types you want to use a function at, and that interacts in some ways also with dictionaries. But as far as I know, like certainly for standard Haskell, there's no guarantee that GHC is free to reorder these arguments. It doesn't matter. So you cannot rely on the fact that the dictionaries occur in the same order as you write them down. But in terms of as far as these type argument passing is concerned for explicit type application, then you get a guarantee that if you write explicit quantification, then you can use the type arguments in that order. But again, that doesn't necessarily mean that the order could not still be flipped in the translation to core. It just gives you a guarantee that within the surface language, the things are treated consistently.
So I understand, I don't know if we've got it yet, we're getting constraint kinds.
We have
constraint kinds.
Yeah.
So that seems to me like it's basically giving some way to make these dictionaries explicit without breaking things like the canonicity of type classes. Is there? Can you elaborate a bit more what the actual mechanism is there?
No, I don't think so. I mean, the constraint kinds in themselves are just a way to take the types apart and to say, like in the same way, let's look at one of these. In the same way as we're saying the list type is a thing of kind star to star, which is applied to an argument here. So this thing is well kinded, and then we're applying the arrow operator, which expects one thing of kind star to the left and one thing of kind star to the right. Essentially, constraint kinds are just saying that constraints are not much different. So morally, you can look at the double arrow as another type level operator that takes something of kind constraints to the left and something of kind star to the right. And you can look at EQ as another type level operator that takes something of kind star and produces something of kind constraint. So all the things that are corresponding to dictionaries have this particular kind. And it gives you a way to talk about them. It gives you a way to do some crazy things like define classes that are parameterized over other classes, or define classes that are parameterized by variable constraints. And that does, to a certain extent, also reflect in the dictionary translation. But I don't think that it directly gives you a way to, for example, define multiple instances of the same type. That is a very different...
And you can't do things like, I mean, they become values, like the actual values of type.
There is a different discussion going on currently among GHC developers whether constraints should actually get kind star. And that would change things quite a bit, because that would be a step towards making the dictionaries visible and inspectable in the surface language, because you could essentially just like treat a class as a type, namely as its dictionary type, and actually pass it around and change it yourself. But I think that would require this change of unifying the kinds constraint and star that is being discussed, but no decision has been made. With just constraint kinds, I don't think that you can easily do it. I think we should probably stop. Yeah. Thank you.